All right, last but certainly not least, we have, yeah, great job, great job. Ben Skopic, he's also a research staff member at, and Hannah Yee, sorry, only one person was listed on the agenda. So they're both research staff members at IDA, one in science systems and sustainment, and the other in operational evaluation. So they'll be talking about SERPENS to assess operational impacts of orbital debris.
Hannah's gonna start.
Yeah. I'll let you guys guess whether I'm Ben or Hannah. All right. Hi, everyone. I'm Hannah Yee. I'm on the research staff at Institute for Defense Analyses, and I'll be co-presenting with Ben on a project we've been working on with our small yet mighty team. So Ben will present some of the technical work later on at the second half of this talk. I'll do the introduction. And then finally, Cameron right in the center is our project leader to oversee everything. So in this session so far, we've talked a lot about orbital debris and how it impacts satellites. So does debris kill satellites? Does it take it down? Why does it take it down? How much debris is made? But actually, when you think about satellite operations, the users of satellites aren't in space on the satellite, it's actually on the ground. And the coverage of, say, our communication systems or our Earth observation systems. And what we'll show today is that even though there is little risk so far about orbital debris killing satellites, that this still has a substantial operational impact to the ground and to our users using our systems today. So going into this as background, the number of objects in space has been growing rapidly since we started launching assets in space, particularly showing in 1 and 2, we have large influxes of objects from debris fragments, from ASAT testing, and then also from collisions between satellite to satellite collisions. In addition, as of recently, there's been an explosive launch in commercial interest in space, which has been growing the number of spacecraft in low Earth orbit exponentially for the past couple of years. So here, orbital debris grows as we're getting more strikes between debris and satellites. And we can ask questions over time and in the future on what's the probability increase in conjunctions between the satellites and debris, and something that Darren's been working on quite well, thank you. And then also how much debris is generated from each of these collisions. What's also not shown here is even if you don't have a collision and you have to do a maneuver, what's the operational impact to the users on the ground and the ground coverage of your satellites? So to do a lot of these, we need to have modeling and simulation tools to look at the entire space environment to understand from the constellation level how operations are affected by the existing orbital debris environment. And what we'll assert today is that our tool called SERPENS is a very nice tool to be able to study these types of simulations. So just to give some background, when it comes to the current debris environment and space environment, here's the publicly published catalog for the low Earth orbit. So in gray, we have the satellites as a function of altitude. So in the big peaks shown here are annotated for Starlink and OneWeb. In addition, from the trackable debris, so items that are about 10 centimeters or a baseball or larger are shown in the blue distribution, where we have a high density of debris in the, let's say, 800 to 1,000 region. And actually, we know that a lot of our satellites today and in the future are in this high debris regime. So things like Iridium and NOAA, which are existing satellite constellations, operate in this high debris density regime. In addition, we also expect to have large planned constellations for DoD and also commercial assets to be operating in this space. So we know that this is a regime that we need to do a lot of satellite operations in. And so what's the effect today? So actually, we do see an effect today on the operations for the past month. So in red is the distribution for the number of conjunction messages that we've seen for the past month, which is on the order of about 1,000 conjunction messages or probabilities of collisions between satellites with other satellite or debris. So shown here, you would have to make a decision, or the operator here needs to make a decision on whether to maneuver, which would affect the coverage if you're doing a very extreme maneuver. Say you have to veer, way right or way left, or do a roll. And this will affect your overall mission coverage. So that's one type of decision that a satellite operator can make. The other option is that you can say, I'm not going to do anything. I'm going to risk the collision. And if you do have a collision here, you can kill the satellite and also generate massive amounts of debris, which will then affect the rest of the constellation. So just for an example, if you choose option 2, or the risk of a collision, here is the amount of debris that we would expect to be generated from this SPHC simulation. So thanks, Pete, for doing a lot of this work for us too. So this is what I would call, for scale, a small hit on small satellites. So this is a 10 centimeter satellite array that we're simulating. And this impactor is just the size of a walnut. So these are very small objects that are colliding with each other that generates a lot of debris. So to model all of this, so the amount of debris generated, the existing debris, the existing satellites, and the number of conjunctions and maneuvers, we developed for the past year a modeling and simulation tool called SERPENS, or Space Environment Risk Prediction, by evaluating numerical simulations. So here we're trying to build a very modular framework to be able to model several types of capabilities shown at the front. And so today we'll talk about how we're doing our orbit propagation, and then also the probability of collision. We're also modeling a lot of different scenarios, not only just the debris generating or kinetic scenarios that we'll present today, but also other RF related or jamming scenarios. And then finally, we'll also discuss, or Ben will discuss, the mission impacts. So how we actually assess this for the operational user by mission availability and satellite field of regard or coverage for a whole constellation. So shown here is just a sample visual of something that we can simulate in our SERPENS code. So we're simulating here a space station breakup, which is modeled in that yellow arrow over there. And honestly, the motivation here was that we wanted to have a scenario where you could see something really clearly. And so I think this one was a very nice choice. Good job, Ben. Okay, so first I'll talk about the propagator, and then I'll let it go to Ben for the rest of the talk on the technical portions. So when we're choosing a propagator or designing a propagator for the SERPENS framework, there's 2 different types of propagators or theoretical frameworks. The first is an analytical propagation. So this is something that you might be familiar with, something like SGP4. And then here, these are closed form solutions. So this is something that's an analytic solution, so that you just input your input values, and it'll spit out all your output value right there. The con here is that it is a complex functional form. So there's actually very few people who really know the analytical form for this one. So you really just download the software, click go, and then you trust that it's correct. And because it's a complex form, if you want to add any types of perturbations, one that we're really interested in is to have orbital maneuvering. That's something that's really hard to then code back in or into the functional form. On the other hand, there's something called numerical propagation, which is an iterative propagation. So here you're integrating the equations of motion to get the position of a satellite or object as a function of time iteratively. So here, this is much more easier to add in these perturbations over time. But it comes at the cost of computation. So this is relatively computationally slow because you have to iterate over the solution several times, whereas for something like an analytic solution, you just rip it in once. Okay, so considering the space for the capabilities between an analytic or like SGP4 or a numerical propagator like SERPENS, we considered several different pros and cons between the two. So obviously in this first one, something like SGP4 is very easy to implement, whereas something like our numerical propagator requires a lot more custom coding. But in general, we chose the numerical propagator because of the flexible framework, that it's dynamic and modular. So something like this, since we're building it from scratch, we're able to add in all the perturbations of interest, number one. And number two, what we're really interested in is doing this dynamic space operation, so doing orbital maneuvers or baking that into our simulation. But actually comparing the two, analytic and numerical, we can compare the two. So something like SGP4 to our current iteration of the SERPENS propagator. And we say that the performance here over one day for the same input parameters are pretty comparable, or I would say very comparable. So shown here is the propagation over a day for SERPENS and SGP4. And if you look all the way at that 1 day mark, the difference there between those 2 points is about 5 kilometers. So when it comes to performance between the two implementations of a propagator, we're seeing very comparable results. So with this, if you have any questions, just save it for after the talk and we can have a really nice conversation. But otherwise, I want to give it to Ben so he can tell you about a lot of the great technical work we're doing.
Thank you, Hannah. Following on with this, I'm going to talk about how we do the conjunction assessments. And so the 19th Space Defense Squadron, they have their whole method designed to do this, and we're modeling our method after theirs. So it's essentially a quantum mechanical state where there are uncertainty bubbles that represent object in space. And so these uncertainty bubbles, they will come and interact with each other, and where they come and interact at their closest, that's the radius of closest approach, and that time is the time of closest approach. So at the time of closest approach, we integrate the area that the two uncertainty bubbles overlap, and that is essentially the probability that those two objects will collide. In SERPENS, since we're looking into the operational capabilities, we are only doing the conjunctions for the satellite to satellite and the satellite to debris potential conjunctions. And then also when objects are within 700 kilometers of each other, that is a function of the time step of 1 minute that we have chosen. So as we said, we're looking into the operational impacts and trying to really understand what a lot of these kinetic effects of debris would be. So the scenario that we're going to be presenting today is a completely notional scenario, and it is a coordinated ASAT attack on the Flock constellation. So the Flock constellation is about 100 satellites, all in a polar orbit around the Earth at between 400 and 500 kilometers. And in this scenario we are making up is that we're saying that all of these 96 satellites will spontaneously explode. So within each one of these explosions, as a lot of the other presenters have shown, is that we are creating potentially thousands of debris objects. We are downsampling to only the 50 most critical debris objects, and then we are running from that. So that's creating about 5,000 new debris objects due to this notional coordinated ASAT scenario. And then on the operational impact side, we're modeling the Iridium constellation. The Iridium constellation has 80 active satellites. They are also in a polar orbit, although at a different altitude. So we're going to see how a potential ASAT scenario at 400 to 500 kilometers would impact a constellation at almost 800 kilometers. So a similar visualization, we have the red dots, which are the currently tracked debris, the white dots being the active satellites, and then these orange dots, these are in a ring around the globe in that polar orbit. That is the Flock constellation. And then the cyan dots, more evenly spaced, but still in polar orbits. Those are the Iridium constellation that we're going to look at the operational impacts on. And then on the right, we have the same histogram that Hannah has shown and Darren has shown before, again, where the satellites and debris are as a function of altitude. And then we're going to see where those debris are coming in on top. And those debris are going to come in at the yellow dots and also yellow bars on the histogram. Okay, so this is going to loop back onto itself in this GIF after 1 hour. And so this is just showing the first hour after the coordinated attack. So at 10 minutes, we'll see the orange dots explode, turn yellow, and very quickly.
What delta V did you add to those fragments?
So this is based off of the NASA model.
What delta V did you add to those fragments?
It was distributed.
What do you mean what delta
Yeah.
V added to? How much delta V? You're having effects out to 1,500 kilometers from a CubeSat blowing up. And so the delta V imparted must be very large. I'm just trying to say what's the maximum delta V that you would give?
Less than 10 kilometers.
10 kilometers per
Less
second?
than. We put 100.
10 kilometers per second, you bring
No.
trajectory. Okay. I just
Not everybody is at this velocity. NASA model, in addition to the size and mass distribution that Pete just shown, there's also a component of the velocity distribution, and we sample from that distribution.
So it's more of a momentum distribution. Yeah. Okay, so within this simulation, we're doing our PC calculations, and using the probability of collision, we're gonna try to make connections to how those will impact the operation of the Iridium constellation. And so this is the coverage map of the Iridium constellation. The green blobs are basically the area of regard for each one of these satellites. And then when they are turning red, this is when we're modeling the probability of the collision being greater than 10 to the minus 8. This is a conservative threshold, but for the purposes of this simulation, that's what we went for. And then on the right, if we wrap each one of these constellations in the individual time at which they are no longer mission available or have a PC of 10 to the minus 8, we're wrapping that all into the whole percent of mission availability. And as a function of time, we're able to predict what that would be. And even though there might not be an actual collision happening within the first hour of this simulation, it's a trade-off between risk and your mission availability. So if you have a higher threshold for risk, then we are able to simulate that with a higher PC threshold, and then that would affect your operation capabilities. So we've built SERPENS as a framework to do more than just debris, and we're able to look at a number of other potential threats in the space environment and also other operational satellites that you'd be interested in. So the Iridium constellation was a communication satellite, although we're building the capability to do ISR satellites. And then also we can dynamically look at potentially future SDA, space domain awareness infrastructure, and test how that would impact your overall operational capability if that PC is naturally shrunk by improved space domain awareness. So we're hoping to start a conversation and see what the needs are in the community, to see what potential customers are interested in having their questions answered. So with that, if you have any questions, I'd love to take them.
Just mentioned a couple times that using the numerical tool can be computationally expensive. Can you quantify that a little bit? Do these take you downsample quite a bit of the debris generated?
Yeah.
And so are these, first of all, are you running these on an HPC? Does it scale, or are you doing this as is this a laptop calculation, and how much time does it take?
So with that simulation, that was about 25,000 objects, and it ran over a few days and just on a laptop.
Is your code written such that it could be scaled to an HPC if you wanted to run the million pieces we were looking at for some of those models?
Yes,
earlier?
exactly. And then get into the non-trackable objects as well.
Right.
Yeah. Yeah.
Excellent.
Have questions? We saw we have about 10 minutes.
Yeah.
So I think when you showed SGP4 versus the SERPENS computer, it matched very well on one day. Is it, when you go to longer timescales, that when you're gonna start to see more of a difference, or is it just, do you expect to have that similar match throughout?
We have seen more of a difference, although SGP4 basically resets with every measurement that is taken. And so that's why we restricted that analysis just for a comparison for one day.
Numerical tools can accumulate error over time.
Yeah. So if we're pretty accurate within one day, and also the simulation that we showed today was only 1 hour. So
Yeah.
we don't expect to see much difference though.
Yeah, I guess in that vein, how the utility of your tool, how long do you expect to model for? An hour, a day, a week?
I mean, at least computationally, that would be restrained by the number of objects. Fewer objects, we can go much longer times. More objects, then it just become cumbersome to go for too long. But I'd expect to be able to go out for longer period of time, I mean years, for a few objects.
Computationally, but
Yeah,
accuracy wise.
we haven't looked into
Okay.
what that would look like at that time scale.
Oh, thank you for speaking.